to start with centripetal acceleration and centripetal force problems. So if you remember from the PowerPoints, a centripetal acceleration and centripetal force occur whenever we're going around a curve, in a turn, in any sort of circular motion. Okay, so with this problem, we have an ATV with a mass of 230 kilograms taking a curve, so that's why it's centripetal force and motion, with a radius of 18 meters at a velocity of 31 miles per hour. So we're going to calculate the centripetal acceleration and centripetal force. So let's start and see if we need to convert anything. So let's look at the information given. So we have kilograms. That's good, we want it in kilograms. For the radius, we have 18 meters. Do we want it in meters? Yes, we do. Now let's look at the velocity. Miles per hour. Do we want miles per hour? We do not, right? What do we need it in? We're going to convert it from miles per hour to meters per second. Okay, so we're going to need that conversion factor that we used in chapter 4. The 0.447 meters per second is equal to 1 mile per hour. Okay, so once you have your conversion factor, you set up your nice little railroad tracks. What's going to go in this top left corner? The original number, the 31 mph. Then we're going to take this conversion factor and place it here. And we want to place it so that the miles per hour is on the bottom, so that mph on opposite sides of this horizontal line, causing them to cancel. That's going to put my 0.447 meters per second along the top. So to calculate the meters per second, we are going to be taking 31 and multiplying it by 0.447. And I'm getting 13.857. And I'm keeping all digits because this isn't a final answer. Okay, so you want to keep as many digits as possible because we're going to be using this in our calculations. It's not a final answer. So I'm going to erase this work and put this as one of my knowns, just to save some room here. Okay, so erasing this. And remember, meters per second is a velocity, right? So this is going to be my V value. So that's 13.857 meters per second. All right. So one of my knowns. What are my other knowns? So looking back, find the numbers in the problem. 230 kilograms. So what is that? It is a mass, an M. If you weren't sure, it says right before it, mass of. Okay, so we have 230 kilograms. The other piece of information, 18 meters. Now we've labeled that as a D so far, as a distance. Okay, but when we're looking at the equations for centripetal acceleration and centripetal force, instead of a D, they write R, because that distance there, that 18 meters, that's the radius of the curve, the radius of the circle. All right, what are we looking for? We are looking for the acceleration and the force. Since they are going around a curve, that acceleration that we're solving for is A sub C, the C for centripetal. Force, same thing, F sub C for centripetal. So we have our knowns and unknowns. Now let's find an equation. The nice thing about these is since we know it's centripetal, we only have one equation for centripetal acceleration, and that is V squared over R. No rearrangement required, so we are just going to plug in our information. Our velocity converted to meters per second, so we have 13.857. We're going to square that and divide it by our radius of 18. So I'm going to calculate that out quick. 13.857, we're going to square it and then divide it by 18. And how many significant figures do we want? Looking at all the numbers present, there is 2 in each number, so we want 2 sig figs in our answer. So it will round up to 11, And what are the units on acceleration? Meters per second squared. Okay, so it doesn't matter that whether it's centripetal acceleration or linear acceleration, the units are still the same. So we have our centripetal acceleration. Now let's solve for centripetal force. Now on your equation sheet, I just kind of want to point out, because I know it might look a little confusing for this equation. So we have two equations actually for centripetal force. This is one, okay, and then I believe there's an equal sign, and then it says MAC. So what that means is you can use either of these, okay? So let me write it a different way so you can see. So this is one equation, this is the other. So the reason you are given two is because if you're given only velocity and radius, then you want to use this equation. But if you're given centripetal acceleration, or in our case, if you've solved for it, you can use the second equation and just do a simple multiplication. That way you don't have to square velocity and divide by radius again like we did over here. So we already figured out that section, right? So this v squared r is just AC, right? So that's how we come up with that. All right, so I'm going to use the second equation here because that's just more straightforward. It's easier to use. And I'm going to plug in my mass over here, the 230, and I'm going to multiply it by the acceleration that I just solved for. And depending which equation you use, your answer will differ slightly, but that is fine because the choices will be close enough where you'll be able to pick the closest choice. So 2530 is what I'm getting. But that is not the answer because I need significant figures. Remember, I just want two. So if I want just two significant figures, 2 is important, the 5 is important. Look to the number next to it. Does that stay a 5? Yes, it does. So 2, 5, and then I still need placeholders for these two spots. So I'm going to put zeros as placeholders so they don't count as significant figures. So it takes 2,500, what are the units on force? Newtons, after Sir Isaac Newton. So it takes 2,500 newtons of force for that ATV to take that curve at that velocity. All right. So let's look at the next problem. You have a fighter jet now, accelerating at 88.2 meters per second squared, and it makes a turn, so we're turning again. So that's why we're looking at centripetal acceleration and centripetal force. It wants us to calculate velocity and centripetal force. So let's start with conversions. Kilograms, is that what we want? Yes, it is. Meters per second squared, good there. And then the radius is in meters. So no conversions necessary. All right, so let's make our list of knowns and unknowns. So we have kilograms. So 27,000 kilograms is what? It's a mass. Then we have 88.2 meters per second. Squared, squared. If it was meters per second, it would be a velocity, but it's meters per second squared. So that is an A, an acceleration. Then making a turn with radius. So remember in these problems, the distance, the meters, is R, not D. All right. So we need to calculate velocity. And what else? Centripetal force, so F sub C. All right, so now we need to pick an equation. So looking at, oh, I forgot a C here, look at my acceleration. This should be A sub C because it's going around a curve, so it's centripetal acceleration. That's going to help you when finding the appropriate equations. So the equation that I need to use to solve for velocity is going to have to be either the centripetal force or the centripetal acceleration. We can't go back and use equations in chapter 4 for that, because chapter 4 was linear motion and this is circular motion. So different equations. So my A sub c equation that I have is v squared over r. So I need to use this to solve for v. So I need to get v by itself. Okay, so we're going to rearrange the equation and then we'll plug in. So to get v by itself, I need to first get rid of this r. I need this r over here. So when this r comes over here, it's going to go from the denominator up to the numerator. Because to get rid of r, I'm going to multiply this side of the equation by r. So that now the r's are going to cancel. Whatever I do to one side of the equation, I have to do to the other. So I'm also going to multiply this side by r. So I have AC times r is equal to v squared. Now, v's by itself over here, but it's still squared, so I need to get rid of that squared. In order to do that, I'm going to take the square root, because that's going to get rid of that superscript of 2. Since I took the square root of this side of the equation, I also need to take the square root of the other side. So now I have v is equal to the square root of AC r. So now I can plug in. My centripetal acceleration is 88.2. I'm going to multiply that by my radius down here at 925. So 88.2, square root of 88.2 times 925 gives me, how many sig figs were we looking at? 2 sig figs there. Oh, but we didn't use that number. So 3 sig figs, 3 sig figs. 3, 3, so we need 3 in our answer. So we're going to have 286, because I'm going to need to round it up. And what are the units on velocity? Not miles per hour, but meters per second. Okay, so going pretty fast, right? It is a jet, so that makes sense that it has a high velocity. 286 meters per second. So let's go ahead and solve for the last variable, centripetal force. So how much force do you think is going to be required to take this turn? Think it's going to be more force than required for that last problem with the ATV? I would think so, because it'd take more force to turn a jet than it would an ATV. So let's calculate and see. So start with our equation, and we can use the version where it's mass times centripetal acceleration, because we have the mass and we have the centripetal acceleration. Okay, we could use this one as well. It's just a little bit more work. We'll get the same answer though. So F sub c, so our mass is 27,000. Our acceleration is 88.2, so we're going to get a huge number. And notice, looking at the numbers we used, we want just 2 sig figs. Okay, so it's different than the answer down here because we use different numbers to solve. So F sub c is going to equal, so we have 2,700 times 88.2. We're going to get a big number. 2 million, I think. 2381400. 1, 2, 3, 1, 2, 3. So yeah, it is 2 million. 2 million what? What's the units? Newtons, after Sir Isaac Newton himself. So this is not done yet though, because we did say 2 sig figs. So remember, on a big number, when we're trying to do 2 sig figs, we start at the left. Those are the 2 we want. Look to the number next to it. Is that going to stay a 3 or is it going to round up? In this case, we are rounding up. And for each of these numbers, we're going to put zeros for placeholders. So the 8 becomes a 0, the 1 becomes a 0, the 4 becomes a 0, and then these 2 zeros also remain. That way, we're still in the 2 million range. Okay? So this would be our correct answer. All right, next we're going to look at gravitational force. All right, so now we're looking at gravitational force. So if you remember on the PowerPoints with gravitational force, that is the force that you are exerting on everything around you and that everything around you is exerting back on you. So these are going to be some pretty small forces. So the last two problems we looked at, we were looking at 2,000 newtons of force and 2 million newtons of force. So we're going to be looking at much smaller numbers here. And I did change these numbers slightly to give them more significant figures, because I noticed there's only one. So I just added a decimal point with a 0 to increase the sig fig numbers. So let's look. Calculate the force of gravity. Okay, so this term right here saying force of gravity, that is F of G. Okay, so this will help us pick the right force equation by looking at clues in the word problem itself. Before I go any further with that, let's check the units on the pieces of information given to us and make sure we don't need to convert anything. So we have kilograms, good there, kilograms once again, and then meters. So good, good, good. Let's do our knowns and unknowns. I'm going to start with that 90 kilograms. So what is that? It's a mass. Then we go to the next number, and it's also a mass, right? So remember, for these problems, it's the gravitational force between two objects. Okay, so you will always have two masses when solving for these problems. So that's another clue that it's the gravitational force that you need to be using. So when we label these, since we have two m's, we label them M1 and M2. And it doesn't matter which one you label M1 and which one you label M2. You'll get the same answer if I would have flipped them. Okay? Now the last piece of information given is this 10 meters. Now this is a distance, but in the gravitational force equation, it's represented by the letter R, because it is the radius between the centers of masses of the two objects. Okay? So if you mislabel it as D at first, that's fine. Once you pick out your equation, you'll realize that radius is the same as D. Okay? R is the same as D. So the only piece of information they're asking us to solve for is F of G. So let's write down that equation. We have capital G, that's the gravitational force constant that is on your equation sheet. And then M1, M2 divided by R2. All right, so notice we have M1, yes. M2, yes. R, yes. This G we haven't written down yet. It is on your equation sheet, but I'm going to write it to the side so that I have it ready for when I start plugging in my numbers. I'm not going to write the units with it because it's just a lot of units. All right. So now I'm going to take all of my knowns and start plugging in. It's going to be quite big, quite large. So I have 6.67 times 10 to the negative 11th on top. That's that gravitational constant. That's going to be used in every time that you calculate the gravitational force. Then I have my M1 of 90, my M2 of 2,000, so that's the vehicle. And then radius on the bottom is 10, but don't forget to square it. Okay, there's that squared there. So now, plugging all of those in, so 6.67, 11 times 90 times 2,000, and then divided by 10 squared. My calculator did not put in scientific notation. 2 times 10 to the 4. 4, 5, 6 zeros, 1, 2. Okay, before I report these, I want to make sure I have the correct number of sig figs. So let me go over here and look. 3, 5, because the zeros count since I added that decimal point at that last minute there. Okay, so I need 3 sig figs. So to get 3 sig figs with both of these, I'm just going to put a 0. What are the units? It's still a force, so it's going to be newtons. So this is just the scientific notation of this answer here. Okay, so either of these answers would be acceptable. All right, so notice, very small number. The last problem we looked at with that fighter jet, 2 million newtons of force was being used. Now we have 0.00000012. Okay, so that's why we don't feel these forces. When you walk by a vehicle, you don't feel its gravitational force on you because it's a very small force. But it's large enough that we can calculate it. All right, let's look at one more problem. So in this problem, we have 2 cars close together, and we're going to calculate the force of gravity between them. So approach it in the same way. Check our units. Kilograms, kilograms, meters. Done. All right, so let's write our knowns and unknowns. So this first number, 2,000 kilograms, that is a mass. The second vehicle is also the same mass. Since we're calculating the force of gravity, we have 2 masses because we're figuring out what the gravitational force is between 2 objects. So I'm going to label them M1 and M2. The last piece of information, that 6.2 meters, that's a distance, but for gravitational force equations, it's represented by the symbol R, the variable R. So that's 6.2 meters. What we're solving for is F of G. So force of gravity is going to be F sub G. With gravitational force, if you don't realize it right away, you will when you write down the equation. We have 6.67 times 10 to the negative 11th is that gravitational constant that will be used every time we solve for this problem. Okay, so our equation, let me write this down again. Let's plug in. You'll notice for this equation, you will not have to rearrange it. Okay, complicated enough as it is, so let's just plug in our numbers. And I would expect, since the masses are now larger, that the gravitational force is going to be larger. Because if you remember from the PowerPoints, that mass and gravitational force were proportional, meaning if one goes up, the other goes up. So these masses have now went up, so the gravitational force will also go up. Okay, so let's calculate and compare to our last problem here. So I have 2,000 times 2,000, and then divided by 6.2. Don't forget to square it. They're also closer to each other than the last problem, so it's definitely going to be larger. 11 times 2,000. Divide that whole thing by 6.2 squared. Sorry, calculator error. I should do these in advance. But it gives you time to hopefully get your calculator out and try them as well. If you see any errors in these videos, please let me know as soon as possible so that I can correct them. Okay. Point 0.0000, so 5 zeros this time, 6941. All right, so before I write that in scientific notation, notice on this problem I didn't add the decimal, the zeros, so we just have 1 sig fig, 1 sig fig, 2 sig figs. So our answer is just going to be to 1 sig fig. Okay, so that would change this into 0.000007. Or if you wrote it in scientific notation, 7 times 10 to the 1, 2, 3, 4, 5, 6, 6th. And a negative 6th. So you want the negative if the number is less than 1. Can't remember if I did that on that last one, hopefully I did. So 7 times 10 to the negative 6th. So this is a larger number than the last problem. So the gravitational force is larger when the mass is larger. All right, so I recommend that you do some of those practice problems on the chapter 4 and 5 homework. The answer key is posted, so you can check your answers on that. And once you've completed that, you're ready to take the chapter 4 and 5 homework quiz that is posted. There are 2 attempts on the homework quiz, so you can do it once, and if you get any wrong, maybe look back at these videos, look at the PowerPoints, rework some problems before you take it that second time.